Circuit definitions node. Any point where two or more circuit elements are connected together. Wires usually have negligible resistance. Each node has one voltage, WRT ground. Branch, a circuit element between two nodes. Loop, a collection of branches that form a closed path returning to the same node without going through any other nodes or branches twice. Example: how many nodes, branches and loops? Plus, Vs is R1 R2 R3 plus VO. Example: 3 nodes plus, Vs is R1 R2 R3 plus VO. Example: 5 branches plus, Vs is R1 R2 R3 plus VO. Example: 3 loops, if starting at node A plus, Vs is R1 R2 R3 plus VO, ABC. Kirchoff's voltage law, KVL. The algebraic sum of voltages around each loop is 0 beginning with one node. Add voltages across each branch in the loop, if you encounter a plus sign first, and subtract voltages, if you encounter a sign first. Sigma voltage drops, sigma voltage rises equals 0, or sigma voltage drops equals sigma voltage rises. Example: Kirchoff's voltage law around first loop plus, Vs is R1 R2 R3 plus VO, ABC I2 I1 plus I2 R2, plus I1 R1. Assign current variables and directions. Use Ohm's law to assign voltages and polarities consistent with passive devices. Current enters at the end side. Example: Kirchoff's voltage law around first loop plus, Vs is R1 R2 R3 plus VO, ABC I2 I1 plus I2 R2, plus I1 R1. Starting at node A, add the first voltage drop, plus I1 R1. Example: Kirchoff's voltage law around first loop plus, Vs is R1 R2 R3 plus VO, ABC I2 I1 plus I2 R2, plus I1 R1. Add the voltage drop from B to C through R2, plus I1 R1 plus I2 R2. Example: Kirchoff's voltage law around first loop plus, Vs is R1 R2 R3 plus VO, ABC I2 I1 plus I2 R2, plus I1 R1. Subtract the voltage rise from C to A through Vs, plus I1 R1 plus I2 R2, Vs equals 0. Notice that the sign of each term matches the polarity encountered first. Circuit analysis. When given a circuit with sources and resistors having fixed values, you can use Kirchoff's two laws and Ohm's law to determine all branch voltages and currents. Plus 12V, I7 omega 3 omega ABC and VAB, plus VBC. Circuit analysis by Ohm's law. VAB equals I7 omega and VBC equals I3 omega. By KVL, VAB plus VBC, 12V equals 0. Substituting, I7 omega plus I3 omega minus 12V equals 0. Solving, I equals 1.2A plus 12V, I7 omega 3 omega ABC plus VAB, plus VBC. Circuit analysis. Since VAB equals I7 omega and VBC equals I3 omega and I equals 1.2A, so VAB equals 8.4V and VBC equals 3.6V plus 12V, I7 omega 3 omega ABC plus VAB, plus VBC. Series resistors. KVL, plus I10 omega, 12V equals 0, so I equals 1.2A. From the viewpoint of the source, the 7 and 3 ohm resistors in series are equivalent to the 10 ohms plus 12V, I10 omega plus I10 omega. Series resistors. To the rest of the circuit, series resistors can be replaced by an equivalent resistance equal to the sum of all resistors. Sigma R series resistors, same current through all, II. Kirchoff's current law, KCL. The algebraic sum of currents entering a node is 0. Add each branch current entering the node and subtract each branch current leaving the node. Sigma currents in, sigma currents out equals 0, or sigma currents in equals sigma currents out. Example: Kirchoff's current law at B plus, Vs is R1 R2 R3 plus VO, ABC I2 I1. Assign current variables and directions. Add currents in, subtract currents out, I1, I2, I3 plus is equals 0 I3. Circuit analysis. 10A 8 omega 4 omega AB plus VAB, by KVL, I1 8 omega plus I2 4 omega equals 0. Solving, I2 equals 2 I1 by KCL, 10A equals I1 plus I2 substituting, 10A equals I1 plus 2 I1 equals 3 I1 so I1 equals 3.33A and I2 equals 6.67A and VAB equals 26.33 volts I1 I2 plus. Circuit analysis 10A 2.667 omega AB plus VAB, by Ohm's law, VAB equals 10A 2.667 omega so VAB equals 26.67 volts replacing two parallel resistors, 8 and 4 omega, by one equivalent one produces the same result from the viewpoint of the rest of the circuit. Parallel resistors the equivalent resistance for any number of resistors in parallel, i.e. they have the same voltage across each resistor. 1 Req equals 1/R1 plus 1/R2 plus 1/Rn for two parallel resistors, Req equals R1 R2 /R1 plus R2. Example circuit solve for the currents through each resistor and the voltages across each resistor. Example circuit using Ohm's law, add polarities and expressions for each resistor voltage plus I1 10 omega, plus I2 8 omega, plus I3 6 omega, plus I3 4 omega. Example circuit write first Kirchoff's voltage law equation minus 50V plus I1 10 omega plus I2 8 omega equals 0 plus I1 10 omega, plus I2 8 omega, plus I3 6 omega, plus I3 4 omega. Example circuit write second Kirchoff's voltage law equation dash I2 8 omega plus I3 6 omega plus I3 4 omega equals 0 or I2 equals I3, 6 plus 4, /8 equals 1.25 I3 plus I1 10 omega, plus I2 8 omega, plus I3 6 omega, plus I3 4 omega. Example circuit write Kirchoff's current law equation at A plus I1, I2, I3 equals 0A. Example circuit we now have three equations in three unknowns, so we can solve for the currents through each resistor, that are used to find the voltage across each resistor since I1, I2, I3 equals 0, I1 equals I2 plus I3 substituting into the first KVL equation minus 50V plus, I2 plus I3, 10 omega plus I2 8 omega equals 0 or I2 18 omega plus I3 10 omega equals 50 volts. Example circuit but from the second KVL equation, I2 equals 1.25 I3 substituting into first KVL equation, 1.25 I3, 18 omega plus I3 10 omega equals 50 volts or, I3 22.5 omega plus I3 10 omega equals 50 volts or, I3 32.5 omega equals 50 volts or, I3 equals 50 volts /32.5 omega or, I3 equals 1.538 amps. Example circuit since I3 equals 1.538 amps I2 equals 1.25 I3 equals 1.923 amps since I1 equals I2 plus I3, I1 equals 3.461 amps the voltages across the resistors, I1 10 omega equals 34.61 volts I2 8 omega equals 15.38 volts I3 6 omega equals 9.23 volts I3 4 omega equals 6.15 volts. Example circuit solve for the currents through each resistor and the voltages across each resistor using series and parallel simplification. Example circuit the 6 and 4 ohm resistors are in series, so are combined into 6 plus 4 equals 10 omega. Example circuit the 8 and 10 ohm resistors are in parallel, so are combined into 810/8 plus 10, equals 14.4 omega. Example circuit the 10 and 4.4 ohm resistors are in series, so are combined into 10 plus 4 equals 14.4 omega. Example circuit writing KVL, I1 4.4 omega, 50V equals 0 or I1 equals 50V /14.4 omega equals 3.46A plus I1 4.4 omega. Example circuit if I1 equals 3.46A, then I1 10 omega equals 34.6V so the voltage across the 8 omega equals 15.4V plus 34.6V, plus 15.4V. Example circuit if I2 8 omega equals 15.4V, then I2 equals 15.4/8 equals 1.93A by KCL, I1 I2 I3 equals 0, so I3 equals I1. I2 equals 1.53A plus 34.6B, plus 15.4B. Circuits with dependent sources. Circuit with dependent sources V1 equals 60 volts because the 20 ohms resistor is in parallel. By Ohm's law, V1 equals I2 20 ohms, so I2 equals V1 slash 20 ohms equals 60 V slash 20 ohms equals 3A. Circuit with dependent sources. If I2 equals 3A, then the 5 ohms I2 dependent source is 15 volts, and if V1 equals 60 V, then the V1 slash 4 ohms dependent source is 15A. Circuit with dependent sources. If circuit with dependent sources writing Kirchoff's voltage law around the outside loop, minus 60 V plus 5 ohms I2 plus 5 ohms I3 equals 0, where I2 equals 3A, so I3 equals 60 to 15, V slash 5 ohms equals 9A. Circuit with dependent sources writing Kirchoff's current law at VI4 plus I3 plus V1 slash 4 equals 0, all leaving node B, since V1 slash 4 ohms equals 15A and I3 equals 9A, I4 equals minus 24A. Circuit with dependent sources writing Kirchoff's current law at AI4 plus I1, I2 equals 0 since I2 equals 3A and I4 equals minus 24A, I1 equals 27A. Circuit with dependent sources. 60V source generating, P equals dash 27A 60V equals dash 1620 watts. 5I2 source absorbing, P equals 24A 15V equals 360 watts. V1 slash 4 source absorbing, P equals 15A 45V equals 675 watts. I1 equals. Circuit with dependent sources. 60V source generating, P equals dash 27A 60V equals dash 1620 watts. 5I2 source absorbing, P equals 24A 15V equals 360 watts. V1 slash 4 source absorbing, P equals 15A 45V equals 675 watts. I1 equals 27A. I4 equals dash 24A. I1 slash 4 ohms equals 15A. V2 equals 45V. Circuit with dependent sources. 20 ohms resistor, VA equals 28 volts. Find I1 2 amps by Ohm's law. I2 14 equals 28. Find I2 2 amps by KCL. For I1 I2 equals 0. Find VB 24 volts by KVL. Dash I1 14 plus I2 2 plus VB equals 0. Find I3 6 amps by Ohm's law. I3 4 equals 24. Find I4 4 amps by KCL. I2 plus I4 I3 equals 0. Sources in series plus, V2 V1 plus V1 plus V2 voltage sources in series add algebraically. Sources in series, plus V2 V1 plus V1 V2 start at the top terminal and add. If hit A plus V1, if you hit A, V2. Sources in series, plus V2 8Vx plus 8Vx V2. If one source is dependent, then so is the equivalent. Sources in series is current sources in series must be the same value and direction is. Sources in parallel I1 I2 current sources in parallel add algebraically I1 plus I2. Sources in parallel I1 I2 current sources in parallel add algebraically I1 plus I2. Sources in parallel I1 5-9. If any source is dependent, then the combination is also dependent I1 plus 5-9. Sources in parallel Vs voltage sources in parallel must be the same value and same direction. Vs plus. Sources in parallel Vs. Source transformation. Source transformation. Source transformation. Practical voltage sources are current limited and we can model them by adding a resistor in series. We want to create an equivalent using a current source and parallel resistance for any RL plus, VSRs RL and VL, IL. Source transformation VL and IL must be the same in both circuits for any RL IP RP RL and VL, IL. Practical source. Source transformation VL and IL must be the same in both circuits for RL equals 0, or a short circuit IP equals IL and VL equals 0 IP RP RL equals 0 plus VL, IL. Source transformation. Now look at the voltage source in series with the resistor with a short circuit. IL equals Vs/Rs and VL equals 0, so IP equals Vs/Rs plus Vs. Source transformation. VL and IL must also be the same in both circuits for RL equals infinity, or an open circuit IL equals 0 and VL equals IP. Source transformation. Now look at the voltage source in series with the resistor with an open circuit. IL equals 0 and VL equals Vs, so Vs equals IP RP. If IP equals Vs/Rs, then RP equals Rs plus Vs. Example, we can transform the voltage source Watt gets all components in parallel plus 20V4A10 omega 15 omega 6 omega plus VO I1. Example, we can combine sources and resistors. E equals 2A plus 4A equals 6A, Req equals 3 omega 20V/10 omega equals 2A 4A10 omega 15 omega 6 omega plus VO. Example, VO equals 6A3 omega equals 18V 6A3 omega plus VO. Example, going back to the original circuit, VO equals 18V KCL, I1 plus 4A, 1.2A, 3A equals 0, so I1 equals 0.2A plus 20V4A10 omega 15 omega 6 omega plus VO equals 18V, 18. Example, we can transform the current source after first combining parallel resistances. Watt gets all components in series plus. Example, we can transform the current source after first combining parallel resistances. Req equals 615/6 plus 15 equals 30/7 omega plus 20V4A10 omega 30/7 omega plus VO. Example, we can now add the series voltage sources and resistances. R total equals 100/7 omega and V total equals 20/7 volts plus 20V1 20/7 V10 omega 30/7 omega plus I1. Example, we can easily solve using KVL for I1. I1 equals 27 divided by 100/7 equals 0.2A plus 20. Voltage and current division. Voltage division. We could have a circuit with multiple resistors in series where we want to be able to find the voltage across any resistor clearly. Req equals sigma Ri, and I equals Vs/Req, so 6 equals I, Ri equals Vs, Ri/Req, plus Vs R1 Rii, Rn plus 6. Voltage division application. You have a 12 volt source, but some devices in your circuit need voltages of 3 and 9 volts to run properly. You can design a voltage divider circuit to produce the necessary voltages plus Vs R1 Rii. Voltage division application. To get 3, 6, and 3 across the 3 resistors, any R, 2R and R could be used. 9 volts is available at A, 3 volts at B plus 12V R2R R plus 6V, plus 9V, plus 3V, plus 3V, AB. Wheatstone bridge. This circuit is often used to measure resistance or convert resistance into a voltage. Plus 100V, 100 omega R 500 omega 300 omega plus VAB, AB. Wheatstone bridge using the voltage divider at A, VAD equals 100 VR/ 100 plus R, omega plus 100 V, 100 omega R 500 omega 300 omega plus VAB, ABD. Wheatstone bridge. Find the voltage at B, using the voltage divider theorem. Plus 100 V, 100 omega R 500 omega 300 omega plus VAB, AB. Wheatstone bridge. VBD equals 100 V 500 omega slash 300 plus 500 omega equals 62.5 V plus 100 V 100 omega R 500 omega 300 omega plus VAB, ABD. Wheatstone bridge. Let's find the relationship between VAB and R. VAB equals VAD, VBD equals 100 R slash 100 plus R, 62.5 plus 100 V, 100 omega R 500 omega 300 omega plus VAB, ABD. Wheatstone bridge. The Wheatstone bridge is considered balanced when VAB equals 0 V. Find R. R equals 167 omega plus 100 V, 100 omega R 500 omega 300 omega plus VAB, AB. Wheatstone Bridge. Current division. What if we want to find the current through any parallel resistor? Req equals 1/sigma, 1/Ri, and V equals is Req, so 2 equals V/Ri equals is, Req/Ri, is R1 Ri Rn plus V, 2. Wheatstone Bridge. The 10A current source divides between the two branches of the bridge circuit 10A 100 omega 100 omega 500 omega 300 omega plus VAB, Di2I1. Wheatstone Bridge. First, simplify by combining the series resistances in each branch of the bridge 10A 100 omega 100 omega 500 omega 300 omega plus VAB, Di2I1. Wheatstone Bridge. First, simplify by combining the series resistances in each branch of the bridge 10A 100 plus 100 omega 300 plus 500 omega I2I1. Wheatstone Bridge. Find the parallel equivalent resistance Req equals 200/200 plus 800, omega equals 160 omega 10A 100 plus 100 omega 300 plus 500 omega I2I1. Wheatstone Bridge. I1 equals 10A, 160/200, equals 8A I2 equals 10A, 160/800, equals 2A 10A 100 plus 100 omega 300 plus 500 omega I2I1. Voltage Vs. Current division. Voltage division 6 equals Vs Ri/Req. Req equals sigma Ri Ri/Req 1 6 Vs. Series resistors only. Current division 2 equals is Req/Ri. Req equals 1 divided by sigma 1/Ri. Req/Ri 1 2 is parallel resistors only. Application. A practical source of 12 volts has a 1 ohms internal resistance. Design a voltage divider that will be used to power up to 10 6-volt light bulbs in parallel. 1 ohms R1 plus, 12 V R2 100 omega 100 omega 100 omega. 10 lights. Application. The voltage across each bulb must be within the range of 5.5 to 6 volts in order for the bulbs to be bright enough. Find R1 and R2. 1 omega R1 plus, 12 V R2 100 omega 100 omega 100 omega. 10 lights. Application. With no bulbs, the maximum voltage is obtained, 12 V R2 1 omega plus R1 plus R2 1 omega R1 plus, 12 V R2 plus V bulb equals 6.0 V equals. Application. The parallel combination of 10 100 omega bulbs is 10 omega. The parallel combination with R2 is 10 R2 10 plus R2, 10 R2 10 plus R2, 1 omega R1 plus, 12 V R2 100 omega 100 omega 100 omega. 10 lights and V bulb, omega. Application. Using the voltage divider and the minimum voltage allowed, 12 V 10 R2 10 plus R2, 1 omega plus R1 plus 10 R2 10 plus R2, 1 omega R1 plus, 12 V R2 100 omega 100 omega 100 omega. 10 lights plus V bulb equals 5.5 V equals. Solution. Solving the two equations simultaneously, R1 equals 0.82 omega and R2 equals 1.82 omega with 10 bulbs, R2 in parallel with 10 100 omega resistors would be 1.54 omega. Using the voltage divider, with 10 bulbs V bulb equals 1 to 1.54 omega divided by 1 plus 0.82 omega plus 1.54 omega, equals 5.5 V. Using the voltage divider, with no bulbs V bulb equals 1 to 1.82 omega divided by 1 plus 0.82 omega plus 1.82 omega, equals 6.0 V. Capacitors and RC circuits. Capacitors composed of two conductive plates separated by an insulator, or dielectric. Commonly illustrated as two parallel metal plates separated by a distance, d. C equals epsilon A/d, where epsilon equals epsilon r. Epsilon O. Epsilon r is the relative dielectric constant. Epsilon O is the vacuum permittivity. Effect of dimensions. Capacitance increases with increasing surface area of the plates, decreasing spacing between plates, and increasing the relative dielectric constant of the insulator between the two plates. Types of capacitors. Fixed capacitors, nonpolarized, may be connected into circuit with either terminal of capacitor connected to the high voltage side of the circuit. Insulator, paper, mica, ceramic, polymer, electrolytic. The negative terminal must always be at a lower voltage than the positive terminal, plates or electrodes, aluminum, tantalum. Nonpolarized. Difficult to make. Nonpolarized capacitors that store a large amount of charge or operate at high voltages. Tolerance on capacitance values is very large, plus 50%/25% is not unusual. P-SPICE symbol. Electrolytic symbols. Fabrication. Variable capacitors. Cross-sectional area is changed as one set of plates are rotated with respect to the other. http://www.tpub.com/need/book2/3f.htm. P-SPICE symbol. Electrical properties of a capacitor. Acts like an open circuit at steady state when connected to a DC voltage or current source. Voltage on a capacitor must be continuous. There are no abrupt changes to the voltage, but there may be discontinuities in the current. An ideal capacitor does not dissipate energy. It takes power when storing energy and returns it when discharging. Properties of a real capacitor. A real capacitor does dissipate energy due leakage of charge through its insulator. This is modeled by putting a resistor in parallel with an ideal capacitor. Energy storage. Charge is stored on the plates of the capacitor. Equation: Q equals CV units, farad equals coulomb/voltage. Farad is abbreviated as F. Sign conventions. The sign convention used with a capacitor is the same as for a power dissipating device. When current flows into the positive side of the voltage across the capacitor, it is positive and the capacitor is dissipating power. When the capacitor releases energy back into the circuit, the sign of the current will be negative. Charging a capacitor. At first, it is easy to store charge in the capacitor. As more charge is stored on the plates of the capacitor, it becomes increasingly difficult to place additional charge on the plates. Coulombic repulsion from the charge already on the plates creates an opposing force to limit the addition of more charge on the plates. Voltage across a capacitor increases rapidly as charge is moved onto the plates when the initial amount of charge on the capacitor is small. Voltage across the capacitor increases more slowly as it becomes difficult to add extra charge to the plates. Adding charge to capacitor. The ability to add charge to a capacitor depends on the amount of charge already on the plates of the capacitor and the force, voltage, driving the charge towards the plates, i.e., current. Discharging a capacitor. At first, it is easy to remove charge in the capacitor. Coulombic repulsion from charge already on the plates creates a force that pushes some of the charge out of the capacitor. Once the force, voltage, that placed the charge in the capacitor is removed, or decreased. As more charge is removed from the plates of the capacitor, it becomes increasingly difficult to get rid of the small amount of charge remaining on the plates. Coulombic repulsion decreases as charge spreads out on the plates. As the amount of charge decreases, the force needed to drive the charge off of the plates decreases. Voltage across a capacitor decreases rapidly as charge is removed from the plates when the initial amount of charge on the capacitor is small. Voltage across the capacitor decreases more slowly as it becomes difficult to force the remaining charge out of the capacitor. RC circuits. RC circuits contain both a resistor R and a capacitor C, D. Until now we have assumed that charge is instantly placed on a capacitor by an EMF. The approximation resulting from this assumption is reasonable, provided the resistance between the EMF and the capacitor being charged/discharged is small. If the resistance between the EMF and the capacitor is finite, then the charge on the capacitor does not change instantaneously. QT. Switch open, no current flows. Charging a capacitor. εR switch CT0 close switch, current flows. T0 I apply Kirchoff's loop rule *, green loop, At the instant charge on C is Q asterisk. Convention for capacitors is like batteries, negative if going across from and to dash. This equation is deceptively complex because I depends on Q and both depend on time. When T equals 0, Q equals 0 and I0 equals epsilon slash R. Limiting cases epsilon R. Switch C. When T is large, the capacitor is fully charged, the current shuts off, and Q equals C epsilon. I. Math. More math. Still more math. RC is the time constant of the circuit. It tells us how fast the capacitor charges and discharges. Why not just solve this for Q and I? Charging a capacitor. Summary. Sample plots with epsilon equals 10V, R equals 200, and C equals 1000 F. RC equals 0.2s. Recall that this is I0, also called I max. In a time T equals RC, the capacitor charges to Q, 1E1, or 63% of its capacity. RC equals 0.2s, and the current drops to I max, E1, or 37% of its maximum. Tau equals RC is called the time constant of the RC circuit. Capacitor charged, switch open, no current flows. Discharging a capacitor R. Switch C. T0 close switch, current flows. T0 I apply Kirchoff's loop rule asterisk, green loop. At the instant charge on C is Q asterisk. Convention for capacitors is like batteries, positive if going across from, to plus. Plus Q and Q. Math, negative because charge decreases. More math, same equation as for charging. Discharging a capacitor. Summary. Sample plots with epsilon equals 10V, R equals 200, and C equals 1000 F. RC equals 0.2s. In a time T equals RC, the capacitor discharges to QE1 or 37% of its capacity. RC equals 0.2s, and the current drops to I max, E1, or 37% of its maximum. Notes this is for charging a capacitor. Epsilon slash R equals I0 equals I max is the initial current, and depends on the charging EMF and the resistor. This is for discharging a capacitor. I0 equals Q slash RC, and depends on how much charge Q the capacitor started with. I0 for charging is equal to I0 for discharging only if the discharging capacitor was fully charged. Summary. This is always true for a capacitor. Final equals CV, where V is the potential difference of the charging EMF. Q0 is the charge on the capacitor at the start of discharge. Q0 equals C epsilon only if you let the capacitor charge for a long time. Ohm's law applies to resistors, not capacitors. Sometimes you can get away with using this. Better to take dq/dt. Capacitors in parallel. CEQ for capacitors in parallel. Capacitors in series. CEQ for capacitors in series. General equations for CEQ: parallel combination, series combination. If P capacitors are in parallel, then if S capacitors are in series, then. Summary. Capacitors are energy storage devices. An ideal capacitor acts like an open circuit at steady state when a DC voltage or current has been applied. The voltage across a capacitor must be a continuous function. The current flowing through a capacitor can be discontinuous. The equations for equivalent capacitance for capacitors in parallel, capacitors in series. Measuring instruments. You know how to calculate the current in the circuit. Measuring instruments. Ammeter, VR. If you don't know V or R, you can measure I with an ammeter. To minimize error, the ammeter resistance R should very small. Any ammeter has a resistance R. Any ammeter has a resistance R. The current you measure is R. Example: an ammeter of resistance 10 is used to measure the current through a 10 resistor in series with a 3V battery that has an internal resistance of 0.5. What is the percent error caused by the non-zero resistance of the ammeter? V equals 3V, R equals 10, R equals 0.5 actual current. You might see the symbol epsilon used instead of V. V equals 3 V R equals 10 R equals 0.5 current with ammeter, RA. A galvanometer http://hyperphysics.phy-asdr.gsu.edu/hbase/magnetic/galvan.html number sign C1. When a current is passed through a coil connected to a needle, the coil experiences a torque and deflects. An ammeter, and a voltmeter, is based on a galvanometer. For now, all you need to know is that the deflection of the galvanometer needle is proportional to the current in the coil, red. A typical galvanometer has a resistance of a few tens of ohms. A galvanometer-based ammeter uses a galvanometer and a shunt, connected in parallel. AIGR shunt IG is shunt I. Everything inside the blue box is the ammeter. The resistance of the ammeter is GR shunt IG is shunt I. Homework hint: the galvanometer reads 1A. Full scale means a current of IG equals 1A produces a full scale deflection of the galvanometer needle. The needle deflection is proportional to the current IG. If you want the ammeter shown to read 5A full scale, then the selected R shunt must result in IG equals 1A when I equals 5A. In that case, what R is shunt and VAB equals V shunt. AB. A galvanometer-based ammeter uses a galvanometer and a shunt, connected in parallel. GR's IG is I. Example: what shunt resistance is required for an ammeter to have a resistance of 10 ohm, if the galvanometer resistance is 60? The shunt resistance is chosen so that IG does not exceed the maximum current for the galvanometer and so that the effective resistance of the ammeter is very small. Actually 0.010002. To achieve such a small resistance, the shunt is probably a large diameter wire or solid piece of metal. Web links: ammeter design, ammeter impact on circuit, clamp on ammeter, based on principles we will soon be studying. Measuring instruments: voltmeter. You can measure a voltage by placing a galvanometer in parallel with the circuit component across which you wish to measure the potential difference. V equals 3 V R equals 10 R equals 0.5 GRGAVV of equals. Example: a galvanometer of resistance 60 is used to measure the voltage drop across a 10K resistor in series with a 6V battery and a 5K resistor. Neglect the internal resistance of the battery. What is the percent error caused by the non-zero resistance of the galvanometer? The measurement is made with the galvanometer. V equals 6 V R1 equals 10K R2 equals 5K GRG equals 60 AV. 60 and 10K resistors in parallel are equivalent to an 59.6 resistor. The total equivalent resistance is 5059.6, so 1.19 x 10-3A of current flows from the battery. I equals 1.19 mA. The voltage drop from A to B is then measured to be 6-1.19 x 10-3, 5000, equals 0.07 V. The percent error is. To reduce the percent error, the device being used as a voltmeter must have a very large resistance, so a voltmeter can be made from galvanometer in series with a large resistance. Example: a voltmeter of resistance 100K is used to measure the voltage drop across a 10K resistor in series with a 6V battery and a 5K resistor. Neglect the internal resistance of the battery. What is the percent error caused by the non-zero resistance of the voltmeter? We already calculated the actual voltage drop, 3 slides back. V equals 6 V R1 equals 10K R2 equals 5K AV. The measurement is now made with the voltmeter. V equals 6 V R1 equals 10K R2 equals 5K GRG equals 100K AV. An ohmmeter measures resistance. An ohmmeter is made from a galvanometer, a series resistance, and a battery. GR SAR R equals. The ohmmeter is connected in parallel with the unknown resistance with external power off. The ohmmeter battery causes current to flow, and Ohm's law is used to determine the unknown resistance. To measure a really small resistance, an ohmmeter won't work. Solution: 4-point probe. VA reference: http://hyperphysics